Okay, so a quick little review here for the sign of sine, cosine, and tangent in each quadrant. You can remember all students take calculus. So moving around from the first, second, third quadrant, all of the trig functions are going to be positive in the first quadrant. Only the sine is going to be positive in the second quadrant. Tangent will be positive in the third quadrant. And in the fourth quadrant, all students take calculus, only the cosine will be positive in the fourth. So if we look here for the first quadrant, the sine, S-I-N-E, should be positive, the cosine and the tangent, so they should all be positive. In the third, the sine and the cosine values are negative, and the tangent will be positive. If we remember that the tangent is sine divided by cosine, a negative divided by a negative is a positive. To find the exact value of the trig functions, so number 3, 4, and 5, we're going to want to remember our unit circle. If we think about pi over 6, if you need to convert that into degrees, you're welcome to do so. So pi over 6 is going to be 30 degrees, or the smallest angle in the first quadrant would be over here. Again, I like to think I'm going to be going out a lot and up just a little bit. So that's going to be root 3 over 2, comma 1/2. Cosine is the x value, so our answer here would be root 3 over 2. For 4 pi over 3, well, you can think about where that might be. For the over 3s, pi over 3 would be about 60 degrees. So 4 pi over 3, we're going to have 1 pi over 3. 2 pi over 3 would be somewhere over here. 3 pi over 3. 4 pi over 3 is going to put us down here in the third quadrant. If we think about our triangle here, and again, it might be helpful for us to convert this into degrees so we can think about 4 pi over 3 in terms of degrees. We'd want to multiply by 180 divided by pi. A little review there. The pi's would cancel. 3 goes into itself once. It goes into 180 60 times. 4 times 60 is going to be 240 degrees. So if we think about where that might be from 180, we're looking at an angle measure of 60 degrees, okay, past that negative x-axis. So in order to get to 60 degrees or 240 degrees to get to our point right here, this is the point, Fallon, that we're looking at, this particular point right here. Okay, to get to that point, we're going to be going out a little bit, so that's going to be negative 1/2, and down a lot, negative root 3 over 2. Now the tangent value is the sine over the cosine, so we have negative root 3 over 2. Negative root 3 over 2 divided by 1/2. So when we flip that fraction, we get negative root 3. It's actually negative 1/2, so it should become positive root 3. So our tangent of 4 pi over 3 is root 3. Now 11 pi over 6, negative 11 pi over 6. One way I like to think about negative 11 pi over 6 is think about a full trip in the negative direction would be 12 pi over 6. So we're almost coming down negative 2 pi and then just bouncing ourselves back up there to have an angle here of pi over 6. Okay, and again, pi over 6 is about 30 degrees, actually exactly 30 degrees. So it brings us right back to our point of root 3 over 2, comma 1/2. Sine value is the y value, so our sine of negative 11 pi over 6 is going to be 1/2. Okay? This unit circle idea is going to be very important as we move into this next section. 4.7, the inverse trigonometric functions. Okay, we're going to look at the inverse sine functions, cosine and tangent. Look at a little bit composing trigonometric functions and inverse trigonometric functions and applications of these inverse trig functions. Okay, the nice thing that inverse trig functions do for us is if they give us a triangle, or we're given a triangle where we have the different sides, we can use inverse trig functions and the ratios of the opposite, the adjacent, the hypotenuse, in order to find the angles in a triangle. First thing to think about, this graph over on the left, this is a piece of y equals the sine of x. Okay. Now we've only been given a piece of this graph. We should know and understand that this graph continues, okay, and it continues in this direction as well. Okay. But using the horizontal line test, so if I was to draw a horizontal line test across the sine graph, we would see that a horizontal line would hit this graph in multiple places. 1, 2, 3, what we're being seen here, what we're being shown here. So what we need to do is we need to limit the domain of the function. And the way we limit that domain is we basically cut off the ends. And we're only going to look at the sine curve from negative pi over 2 to pi over 2. Now what we have over here is the inverse function. Okay, so you can see here that we've basically switched the domain and the range. So where the x values used to go from negative pi over 2 to pi over 2, the y values now go from negative pi over 2 to pi over 2. And where the range of the function used to be negative, or is negative 1 to 1, the domain of the inverse is now negative 1 to 1. Okay? So again, that's that idea of switching the x and y's when we talk about a function and when we talk about its inverse. Okay? So the inverse sine, also called the arc sine. Okay, so there's two different ways to denote this function. Typically, we're going to see inverse sine, but we might also see arc sine. In my mind, the inverse sine typically refers to a degree measure, and the arc sine is typically referring to an arc length or a radian measure. Okay, the domain of the inverse sine function is negative 1 to 1, and the range is negative pi over 2 to pi over 2. These numbers and these windows here come from those graphs that we looked at on the previous slide. So it's important now, we've kind of looked at a few different domain problems. We looked at square roots, we looked at denominators, we looked at logarithms. Now when we look at the inverse sine function, so if we have the inverse sine of some value x, okay, the only numbers x can be are from negative 1 to 1. Okay? So if you try to put in a value of the inverse sine of 2, you're going to get an error message here because that does not exist. Okay? And again, if you think about your sine curve, the sine value has to be between negative 1 and 1. If you think about the boundedness of the curve, if you think about the unit circle, the y values will never go below negative 1 on the bottom and never go above positive 1 on the top of your circle. Okay, example here, evaluating an inverse sine. So we have the inverse sine of negative 1/2. So basically, the way I read this question is, what angle has a sine value of negative 1/2? So I like to think of my unit circle. Okay, I like to think of my unit circle here. Okay. Now, if we look back here on the previous slide, we know here that the range, the output, we're only going to be able to get answers from negative pi over 2 to pi over 2. So basically, I'm only looking now at my first and fourth quadrants. So none of this stuff is going to exist now when I'm thinking about the inverse sine. So now I have to think, what angle has an inverse sine of negative 1/2? Sine is the y value. So y value of negative 1/2 would mean that I'm going out a lot and down a little. Okay, so this would give me the value of root 3 over 2, that's the cosine value, comma negative 1/2. So since I'm looking at this angle right here, this is going to be 30 degrees. Okay, and since my answer has to be between negative pi over 2 and pi over 2, I'm thinking negative 30 degrees. But since they want that to be written in radians, I'm going to go ahead and I'm going to look at negative pi over 6, because converting negative 30 degrees into radians, I multiply by pi over 180. And we can see here that we're going to cancel down and reduce into negative pi over 6. We can verify this on the calculator. If we put in inverse sine of negative 1/2 on the calculator, so we're going to use the second sine button, and negative 1/2. I'm going to make sure that I'm in degree mode, just so that it'll be a little bit easier for us to see our answer. And I get negative 30 degrees, which is the same answer that I got using my unit circle. So find the exact value without using the calculator. The inverse sine of the sine of pi over 10. So this is kind of an interesting question, because this is basically saying I'm doing f inverse of f of x. So if we remember our composition rules, f inverse of f of x, okay, we looked at it like this. Okay, this should be equal to x, in which case our answer here will be pi over 10. What this question is saying is there's an angle, pi over 10. What is the sine of that angle? We can call that x. And then what is the inverse sine of that x? Well, it's going to take us right back to our pi over 10, which is where we started from. We do want to make sure that our answer of pi over 10 falls within the acceptable range of answers from negative pi over 2 to pi over 2, and pi over 10 satisfies that, so pi over 10 is our answer. Okay, the inverse cosine function, similarly we have to limit the domain, okay, of the cosine function so that it will pass the horizontal line test. We're going to limit that domain from 0 out to pi. And then once we've flipped the inputs and the outputs, swapped the domain and the range, or reflected this graph over the line y equals x, we get our inverse function. So here's the graph of y equals cosine of x, and here is your graph of y equals inverse cosine of x. Okay? These graphs are not very important, okay, in terms of the actual graphing of the inverse functions, but it is important to realize why we need to limit the domain of the cosine, which then in turn limits the range of the inverse cosine. Okay, so again, similar notation, inverse cosine, arc cosine. Okay, we have an angle now that has to be between 0 and pi. So now when we look at inverse cosine functions, we're going to be talking about only the first and second quadrants. Okay, so your acceptable answers will be in the first and second quadrants. Okay, from 0 to pi. Inverse tangent function, again, similarly, we're going to have to limit the domain so that will pass that horizontal line test, which is then going to limit the range for the inverse tangent. So again, here we have the tangent of x. Okay, and we can see that the domain's being limited from negative pi over 2 to pi over 2. And on the right, we have the inverse tangent of x. And now our range is being limited from negative pi over 2 to pi over 2. So similar to the sine curve, with the inverse sine, your answers, your outputs are going to be limited between negative pi over 2 to pi over 2. You'll see in the tangent curve, because we have an asymptote going on at the pi over 2 and at the negative pi over 2, we'll never actually include those values in our outputs for the inverse tangent. Okay. So whereas the sine, we would have a bracket, with the inverse tangent, we're going to be looking at a parenthesis. Okay. So here's your rules again. We're going to be looking at angles from negative pi over 2 to pi over 2. The domain, the inputs, you can have tangent values going from negative infinity all the way to positive infinity. So whereas the inverse sine and inverse cosine are limited to inputs from negative 1 to 1, the inverse tangent. You can find the inverse tangent of any angle or any value you want. Not any angle, any value you want. The angles you'll get out will always be between negative pi over 2 or pi over 2, which is negative 90 or 90, if we want to think about that in terms of degrees. Okay. End behavior, here's that asymptotic behavior that we described in the previous slide. Okay, composing trig functions with arc sine. So what we're given here is a triangle here where we're given the hypotenuse. We're given the opposite side if we're using theta as a reference point. So if we're going to use this triangle to find the required ratios, we want to find the sine of the inverse sine of x. So what angle in this triangle has a sine value of x? So I read this part right here. What angle has a sine value of x? So if you look at the angle theta, sine is the opposite over the hypotenuse, so the opposite would be the x, the hypotenuse would be 1. Now what angle has a sine of x over 1? That's going to be theta. What is the sine of theta? Well, the sine of theta is the opposite over the hypotenuse, so our answer here will just be x. Now we already know that this part is basically telling us that we're now talking about the angle of theta. So what is the cosine of theta? Cosine is the adjacent over the hypotenuse. So that's going to be the square root of 1 minus x squared over 1. Again, inverse sine, this is basically just telling us that we're talking about the angle of theta. And what is the tangent of theta? Tangent is the opposite over the adjacent. So that's going to be x divided by the square root of 1 minus x squared. Okay. We should rationalize that and bring the square root of 1 minus x squared up top of the denominator. But we didn't do that in this particular problem, but a better answer would be x square root of 1 minus x squared over 1 minus x squared. Now, for cosecant, we should just have to take the reciprocal of the sine value, so that should be 1 over x. Secant, we should be taking the reciprocal of the cosine, and again, it'd be beneficial for us to rationalize this, so we'd have the square root of 1 minus x squared over 1 minus x squared. And cotangent, we should be able to take the reciprocal of tangent, and if we flip the tangent, we have square root of 1 minus x squared over x. Now, more interesting problems will give us something like this, where we might have 1, we might have u. Using the Pythagorean theorem, we can find out that this would be u squared plus 1 squared, so u squared plus 1. And now we can use all the trig functions for this. Okay. Now, using this idea, if we were given a problem and it said find the cosine of the inverse sine of, let's just say 1 over x. Okay. So again, inside the parentheses, that says what angle has a sine value of 1 over x. So let's create ourselves a triangle, a right triangle. We're going to call this angle theta, and we're going to set that angle up theta. We're going to set that triangle up so that theta has a sine value of 1 over x. So the opposite divided by the hypotenuse, so the opposite divided by the hypotenuse is 1 over x. Okay. Now to find this remaining side should be, we can call this whatever we want. Let's call it the adjacent, just for fun, because it is the adjacent. So using the Pythagorean theorem, we have the adjacent squared plus 1 squared is equal to x squared, hypotenuse squared. So this adjacent is going to be equal to x squared minus 1 square rooted. Again, you would think plus or minus, but since we're talking about a side length in a triangle, we know that we're going to just go with the positive. So we have x squared minus 1. And now since I'm trying to find the cosine of this angle, cosine is the adjacent divided by the hypotenuse. So adjacent divided by hypotenuse in this case would be the square root of x squared minus 1 over x. One last example that I'd like to look at. We're going to take the angle of 300 and let's take 300 degrees. Okay. we're going to take 300 degrees, and we're going to look at the cosine and the inverse cosine. So since we have a cosine and we have an inverse cosine, our answer, okay, would appear at first glance to be 300 degrees. Okay. But we know that cosine, the acceptable range of outputs for the inverse cosine function, has to be between 0 and pi. If we translate that into degrees, we're looking at answers between 0 and 180 degrees. Okay? So the problem that we run into is 300 is not in that acceptable range of outputs from 0 to 180 degrees, so we have to reevaluate this problem. So if we look at the 300 degrees on the unit circle, 300 degrees would be here. Okay, so that's our 300 degree mark, which leads us to this being 60 degrees, negative 60 degrees. So we can think about, to get to 60 degrees, I'm going to go out a little bit, which is a half, and down a lot, which is negative root 3 over 2. Okay? So the point there is 1/2 comma negative root 3 over 2. So what we need to do is we need to find out where else is the cosine value, or the x value, positive 1/2. Okay? So we know we have another angle up here that would have a cosine value of 1/2, and this would now be positive root 3 over 2. So our answer here, our final answer, is going to actually be 60 degrees. Reason being, the cosine of 300 degrees is the x value, which is equal to 1/2. Okay, so that's 1/2. And then the inverse cosine of 1/2, what angle has a cosine value of 1/2? Again, in the acceptable portion of the unit circle, we're looking at 60 degrees. We can do that into the calculator as well. So if we do the inverse cosine of the cosine of 300, again, I want to just double check to make sure my mode is in degrees, and I get my answer of 60.